I hope you all had a good week and we are rested coming back. We're going to continue talking about some of the components in spectroscopy. And, spectroscopy, as you well know, it's a vastly involved kind of technique. There are many different types of spectroscopies, and we said it's all dependent, on the type of electromagnetic radiation that is being used. You've got X-ray spectroscopy, you can do UVV spectroscopy, which is often what's called the optical spectroscopy. You can do IR spectroscopy, you can do microwave, and so on. So all those are different types of spectroscopies. And of course, they share very similar types of components. And I think we talked about the light sources before. We also talked about different types of components of monochromators. And today, we're going to talk about different types of detectors. Now, of course, as you would imagine, detector is possibly the most important component, because it's the one that's converting, the light into an electronic, component. It's what you refer to as, the photon input transducers, which is going to convert the photon, because you're dealing with electromagnetic radiation. And yet we are dealing, with electronic components as far as instruments are concerned. And so you need to convert that light, into current or voltage or something that is in the electrical domain. And so as you would imagine, as far as the figures of merit are concerned, the type of detector that you use highly impacts the sensitivity of your instrument, and such that what I'm saying is a very, very important component, in the instrument. Now, there are many types of detectors out there, but you would realize actually most of them are based on what you refer to as the photoelectric effect. And the photoelectric effect, refers to, where you take light, which is electromagnetic radiation, and you impinge it, on a material that releases, current, as a result of that impingement. And that is what you refer to as, photo, coming from photon, electric, electric, are the electrons, that are generated. Now, so for the UV spectrometers, you would see these are the most common types of transducers. And one of it is a photovoltaic, which is not very different, from the solar panel, the solar cells. They are the phototubes, which we're going to talk about. Again, totally based on the photoelectric effect, the phototubes. And if you multiply components or if you multiplex phototubes, that is, you add many phototubes together, you refer to that as photomultiplier, type of detector. Now, the other type of photon input transducer, is what you refer to as the photodiodes or the photoconductive, materials, which we're going to talk about. Now, those are for the UVV detectors. Now, for the IR detectors, they are a bit different. And of course, the reason they are different is UVVs, is fairly energetic. If you look at, the type of quantum transitions that are taking place when you take a UV type of electromagnetic radiation and you impinge it, on a molecule or an atom, you see that there will be electronic transitions, meaning the valence electrons will be transiting, to a higher energy level. Now, for the IR or heat, the energy is not big enough, to cause electronic transitions. And as such, you cannot use things like photomultiplier tubes, as detectors for the IR. And so the type of detectors typically used for the IR are the temperature transducers. We've talked before about the thermocouple, very, very common type of transducer for the IR. You can also use bolometers, which are not very different, from the thermocouples. The only difference is bolometers, you're measuring the resistance, of a conductive material. And the last type, of IR detector is what you refer to as a pyroelectric transducer, which is based on what you refer to as a pyroelectric effect. And we're going to talk about that. So first, let's talk about, the vacuum phototubes, for the UVVs, type of, for the UVVs type of spectroscopy. Now, it's very important, that you be able to explain, how these types of components actually work, and the chemistry or the physical chemistry at play, to generate the effect that you are looking for. So for the sake of exams, and also I think to be able to totally understand your instrument, it's important to understand the basis, the working basis, of some of these components. And so the vacuum phototube, I've shown the picture of it here. As the name suggests, all what you have is a tube. And in that tube, you've got a plate of cathode, or you've got an electrode plate, okay? And the electrode plate, in this case, is a cathode. Now that cathode, you coat it with a material that is fairly easily ionizable when it is impeached, with a photon beam. And if you look at the periodic table, you can easily tell what type of materials are easily ionizable. And so look at the periodic table and look at the term which you know from the chemistry 102, ionization energies. Okay? And so if you look at the ionization energies of the group 1 and the group 2 type of elements, you're going to realize that they've got a fairly low ionization energy, meaning that they don't need a lot of energy from a photon, to cause the release of that electron. And the reason, of course, the alkali and the alkali earth metals have got fairly low ionization energy is because they've got only one valence electron that is fairly far from the nuclei. And as such, it can be knocked off, because it is fairly lightly held or lightly attracted, to the shielded nuclei. And so, yes, ionization energies, of the alkali earth metals and the alkali metals are fairly low, and typically those are the materials that you actually use to coat on the cathode, to make this material, or rather component called the vacuum phototube. And so because of that, the photon beam impinges of an alkali coated cathode, and that generates current. And the current, is what is measured, by amperometer, and so forth. Okay? And so that's the basis, of what you refer to as, the photoelectric effect. Now, these types of materials that have got fairly low ionization energy, sometimes we call them photoemissive type of materials. And I've just explained what type of materials they are. One big disadvantage, with the vacuum phototubes is that even when the instrument is idle, you always have, a little bit of current, that is that is being transmitted. And the reason for that, is referred to as the dark current. The reason for that is because there's always some bit of stray light, okay? And the stray light, could be coming from the lighting in the room. And if it penetrates, through the joints in the instrument and ends up, into this photoemissive material. So you've got always this dark current, that contributes to the background signal, of your instrument. The background, maybe I'm gonna call this time, the background signal of your instrument. So this one is a typical type of noise that is always present, with a vacuum phototube. I've already explained, the type of materials, that consist of the photoemissive materials that are used to be coated on the cathode. And as I've said, most of them, are alkali metals, things like potassium, things like cesium, and so on, and the alkali earth metals as well. And the reason for that, again, I've said, they've got fairly low ionization energy, and they don't require a lot of light, to cause electrons to be generated. Now, in most cases, we are dealing with very low amounts of light. Remember, the light, the light that is, the light source, is monochromatic, right? Dealing with, say, a holocathode lamp, or you're dealing with a laser. It's a monochromatic beam. So the energy, maybe you're going to call it the PE, the energy is very, very small. Okay? And so you would expect then, that when this energy or this light impinges, on the photoemissive material, you generate, a very small, amount of current. Okay? And the current, of course, is coming from the electrons, that are generated. Now, for the sake of improving the limits of detection or the sensitivity, of your instrument, you really need to amplify, this type of very small current that is being generated from this very small amount of monochromatic beam of radiation. And so how do you do that? You do that by what you refer to as multiplexing. And so if you take the photon of the vacuum phototube and multiplex it, meaning you join many of the vacuum phototubes, then that's a classic way of amplifying, the current. And that is that's what we refer to as a photomultiplier tube, and is the most common, type of detector out there for the UVVs, spectrometers, because it's very, very sensitive, because you've multiplexed, different or rather numerous, type of vacuum phototubes. Let me try to explain how it works, based on this figure, that is here. Now, one vacuum phototube, often you're going to see some experts calling it a diode, okay? And the reason why sometimes they call it a diode, is because it's connected, to a power supply, often a DC power supply of a certain polarity. All right. So D refers to as the vacuum phototube, which we already talked about, which essentially is just a cathode, that is coated with a photoemissive material. So think about it, if at all I've got a photon of light hitting the first diode, D1, then you generate, a set of electrons, coming from the photoelectric effect. If I accelerate, those electrons, to the second diode, D2, then those electrons impinge on that on that photoemissive material, to generate even more, electrons, which I can accelerate, to the third diode. And because of that, equally I get an amplification, because of impingement, of those electrons, to the third diode. And so maybe in that case, I'm going to say e to the power of 8. And on, I accelerate them, to the fourth and the fifth and the sixth diode and so on. And in the end, what I'm going to have is a cascade of electrons, that only came from a single photon, but in the end, I'm gonna have up to 1 million electrons that are generated from a single photon, and as such, you can see why it's a very, very sensitive type of detector, and actually the most common type of detector out there. So let me clarify something. I've talked about accelerating the electrons, okay, to diode 2 and then accelerating, the resultant electrons to dynode 3 and dynode 4 and so forth. Why do you think, or how can I do acceleration of electrons? Now, the acceleration of electrons is just based on applying a high voltage, a high positive voltage to that particular dynode. So you can see, based on this setup here, dynode 2 has got a high positive voltage compared to dynode 1. Dynode 3, has got, say, plus probably, 550 V. Dynode 5 plus maybe 80 V. And so for that reason, the electrons, keeps getting pulled, to impinge, onto those dynodes. And so that's how actually you move electrons or even any charged particles, and we're going to talk about this in mass spectroscopy. The way you move ions or any charged particle, through through a tube, for example, or into a detector. Basically, you do that by applying a positive voltage in the case of electrons. But in the case of positive ions, you apply a negative voltage, and that way you are able, to electrostatically pull, those charged particles in the direction that you want them to go. Hopefully that's very clear, the PMT. I'd like you to understand how it works and so forth. So the other type of UVV type of detector is what you refer to as silicon photodiode. I think you've heard us talk about PDA, or photodiode array. Photodiode array. It's a type of detector. And these type of detectors or photodiodes, they are based on this group of elements here, group 13, group 14, group 15, which are really, I've got semiconducting, properties, particularly, the group 14. And the most important one, as you would imagine, is a silicon. Silicon is what is used to make, the photo, the photocells and so forth. And in this case, we are actually using them, to make the detectors or the photodiodes. Okay. But take note of this, the way it works with these photodiodes, and maybe some of you have heard about, the PN diodes, they refer to as, the silicon, being doped, okay, with, say, something like aluminum. And that would be, a P type of diode. Now, whereas while silicon is doped, with, say, phosphorus, which is in the group 15, that one is referred to as the N type of diode. And you can see what's actually happening. If I dope silicon with alumina, what is actually happening is that the silicon alumina, combination is going to create pockets of holes or electron deficient vacancies, within that material. And on the other hand, if I dope it with phosphorus, phosphorus has got more electrons, it means that I'm gonna have a lot more electrons, within that material. And that is what I'm referring to as the N-doped, type of diode. Okay? And that is what I have here. I've got the P-type, that is connected, to the N-type. As I've tried to explain the P-type, because it has been doped with alumina, which has got less electrons, and so it's got more pockets of electron deficient holes, it will be more positively charged. On the other hand, the N-type, which is doped with something like phosphorus, it will have an excess of electrons, and this one is gonna have an excess of holes. And holes rather mean, electron deficient areas. Now, if I take that P-type diode, and I connect it to a charge, a power supply, where this side of the P I connected to the negatively charged, and the N side, I connected to the positive terminal of a battery. What I have now is what you refer to as a reverse biased PN type of diode, and it actually behaves as a capacitor, because it is holding charge, inside that material, and there will be no current, that is flowing. There will be no current that is flowing. However, if at all I've got electromagnetic radiation impinging on that diode, I'm gonna cause promotion of electrons, from the valence band, to the conductive band, and that is gonna cause, the movement of electrons to actually happen. And I hope that's fairly clear to us, guys, that anytime you have a semiconductor, and you impinge it with light, the effect of semiconductors is that you've got electrons, that are in the valence band, okay? And you can promote them, to what you refer to as the conducting band, In the conducting band, the electrons freely flow. And for that reason, there's electricity, that is being generated. And so that's what's happening in this case, the promotion of electrons into the conducting band, from the valence band. And that causes this capacitor, now to generate, electricity, that you are measuring, and that is going to be your signal. One huge advantage, of using silicon photodiodes is, as you would expect, is that you can make them very, very small. You can make them very, very cheap. They use very little amount of energy. As you well know, with the light emitting diodes, the principle is the same. The light emitting diodes, the principle is exactly the same. And we know that they produce, or rather they consume very little amount of energy. And as such, this type of detector is very, very good, for portable type of spectrometers, which you want to take to the field, because you don't need a very high charge supply. You can just use batteries and so on. And yet, they're still fairly sensitive, but not as sensitive to a PMT, the photomultiplier tube. They are not as sensitive compared to a PMT. So be able to explain the advantages and the disadvantages of some of these components. In fact, in an exam setting, I can ask you, to build a spectrometer justifying every component, that you use, for a certain purpose for that in a spectrometer. So, for example, I can ask you, to make a fairly miniaturized, a fairly small, portable spectrometer that you can take to the field where there is no power, where you do not have electricity. And so as such, you have to justify the choice of any material, that you integrate, into that portable spectrometer. So be able to understand the basis of all these types of devices. Now, let me talk a little bit, about what you refer to as a multi-channel, photon transducers, okay? Now, I think I previously told you that when you're dealing with, say, a grating, at any point in time, you are only having one beam of light, exit, through the exit slit. Okay. For example, assume, you're doing, say, visible spectroscopy, of a compound, such as chlorophyll. Chlorophyll. I think I spelled it wrong. Chlorophyll. And we know chlorophyll, typically would absorb, from around 400 nanometers, to say around 750, nanometers. And so the spectrum of light, that you get, that is wavelength, maybe that's intensity or absorbance, let's say, you're going to get something like that, from 400 to 750 nanometers. Okay, but how are we able, to generate this kind of spectrum? All right, yet we can only detect one beam of light at any given time. So we said to do this, you can either rotate the grating so that at any given time, you've got only one light source, that is actually going through, the exit slit. Alternatively, you can open the exit slit and then you have a multiplex of detectors. And then the light, that is coming from the grating is hitting this series or an array of detectors. And that way, you would record the entire spectrum simultaneously. So take note of those two approaches, of recording, a full spectrum. You can either rotate the grating, and so that one is what's called scanning. Now, scanning takes time. Okay, scanning is going to take time to acquire, the full spectrum. Now, the other approach is, you can just simply, open the exit slit, and then you lay a series of detectors. And that series of detectors is going to record, your entire light, in one go. As you're going to record, simultaneously, your spectrum. And that is the basis, of multi-channel photon transducers, meaning it's an array of detectors that afford acquisition of a full spectra simultaneously, rather than, doing the rotation of the grating or scanning the instrument and using a single type of detector. Now, there are different types of photon transducers that are multi-channel out there, and of course they are all based on what we've just talked about, only that you are creating an array of what we've just talked about, be it the PMTs, you just make an array of them, or be it the photodiodes, you just make an array of them. But before they came to be, one oldest type of multi-channel photon transducer is what you guys well know, the photographic silver film. The people use the Kodak, the Kodak film. All right, it's a classic example, really, of a very old type, of a photon transducer, where light, falls onto a silver material, there's oxidation and so on, and then you can develop, that material, and then there are darkening of zones, that they were not impeached, with the radiation. But of course, that one is not a very sensitive, type of a detector. And so my focus really, is a modern types of multi-channel detectors, which are an array, of the photosensitive elements that I just talked about. Now, one example, of this, is a photodiode array, whatever I just talked about in the previous slide, the photodiodes, only that you make it into an array. And that's why we are calling it the photodiode an array. It's an array, that is printed, on a silicon platform, but then you've got multiple, types of detectors. Now, another type of detector, that is a multi-channel detector is what you refer to as the charge transfer devices. And the charge transfer devices, they're very similar actually to a photodiode, as I'm gonna show you. In fact, they are photodiodes. The only difference, is how you actually acquire, the signal, from these charge transfer devices. If you take your camera, your cell phone, the camera really is a CTD, is a charge transfer device. And there are different types of charge transfer devices, again, as I've said, based on the way you acquire the current, the mode of operation. There's what you call the charge couple device, and there's what you refer to as the charge induced devices, and we're going to talk about them in the next slide. But first, very quickly, the photodiode array. As I've said, the photodiode array is just a series, of the PN PN type of diodes, that are simply in an array. So just a multiplex of PN diodes. And because you can make them really, really small, especially using this technique of photolithography and so on, you can make up to 1,000 diodes on one plate. And so it becomes fairly easy, to acquire a full spectrum with these large set, of diodes, okay? And sometimes you refer to it, as a polychromator, because you're acquiring, a full spectrum simultaneously, so just take note of that. And so one huge advantage, as I said, with the photodiode is that you use very, very low power, and of course you're acquiring, the full spectrum, at the same time. As I've said before, photodiodes, cannot compare, to a PMT, which is a lot more sensitive. So the charge transfer devices, which again, as I said, they are examples of modern multi-channel detectors. Now, they operate in two different ways. Again, all what it is, it's a PN diode. And this PN diode has been printed, with an array of electrodes on the surface of it. And of course, electrodes are typically, connected, to a power supply of a certain polarity, okay? Meaning, when light impinges, on these diodes, as I said before, you generate electrons or holes, and the holes, can get attracted, to a negatively, charged electrode that is printed on the surface of that diode. Okay. Now, of course, I can move, these holes, to the next type of electrode, that is printed, on the surface of that diode, just by switching, the voltage. If I increase this voltage, for example, to minus 25 V, these holes are gonna very quickly, move, to the next, electrode that is printed. And so the charge transfer devices, therefore, you can have what you refer to as the charge induced device, or you can have the so-called charge coupled, device. Now, the charge coupled device is where you are actually measuring So the charge coupled device, is where you're measuring, the charge, as you're moving, these holes, to what you call the charge amplifier. Okay. So the charge coupled device is where you keep moving these holes, to a charge amplifier. But as I said, you can operate it as a CID, where you're just simply measuring the voltage, the potential difference, as you move these electrons from one electrode to another. Okay, so you just move the electrodes, rather you just move the holes, because of the change of polarity, and because of that, there's a potential difference that is created, as you move, those electrons or those holes across two sets of electrodes. And so in this case, you're measuring the voltage. In this case, you're measuring the charge. In CCD, you're measuring the charge. And so as I've said, the CID, you're measuring the voltage change as you move the holes of the electrons. And with the CCD, you are measuring the charge as you move those holes or the electrons, to a charge sensing amplifier. So take note of this then, with the CCD, you are destroying the signal because I'm moving the holes, to a charge amplifier. But very important, with the CID, I'm actually not destroying the signal. So it's a non-destructive signal detection technique, because all I'm doing, is that I'm moving the holes, to the next electrode, and then I can move them back if I so wish, just by changing the polarity, of the electrodes on the surface of the PN on the PN diode. And as such, in this case, you can actually amplify the signal, because you're not destroying it, so you can collect, the signal possibly in a minute, and then you do the measurement. But with a CCD, it's more difficult to accumulate the signal, because anytime you try to measure the signal, you are destroying that charge, because you are making it transition, to a charge amplifier to do the detection. So the CTD, CCD or the CID, very, very common, type of, detectors, and very, very sensitive. Like you guys used the ICP-OES in the lab, and you're going to see what is present is actually a CCD. That's a type of detector, that is there. Your cameras as well on your cell phones, they are based really, on a CCD, kind of technology. So again, you can see, the importance of these types of platforms, for many different types of applications. And if you understand how they work, you can actually create other novel, types of innovations. You can apply them, in a different types of setting, and that becomes, fairly innovative. So understanding is fairly critical of how these things work. So that's all that I'm gonna say, about UVVs types of detectors. So the other types of detectors that I'm gonna talk about is the IR transducers. And as I said, IR is not energetic enough. Is not energetic enough, to cause an electronic transition. And that's why we need a different set of detectors, for the IR. So there's what you refer to as a thermodetectors. There's also what you refer to as a pyroelectric IR detectors. And lastly, there's what you refer to as a photoconducting detectors, which are the photodiodes. Photodiodes can still be used in this case because the energy gap between the valence band, and the conducting band is fairly small, and so it's energetic enough for just the semiconducting materials. So the thermodetectors, that are commonly used are the thermocouple, and I talked previously a lot about the thermocouple. The thermocouple, as I said before, is essentially two dissimilar wires, glued together. Okay, so if at all I take copper and I have chromium or chrome, if I glue them together, because there will be differential conductivity, between those two metals, I'm gonna create, a potential difference if at all I impinge it with heat, and so that's gonna create a voltage, and that is the thermocouple. Bolometer, on the other hand, is very similar, to a thermocouple. The only difference is, in this case, I'm measuring the change of resistance, of these wires. The change of resistance is what I'm measuring, rather than, the change of voltage. But they're very, very similar, to a thermocouple. Now, the other type of detector is what you refer to as, pyroelectric detectors, which are based on these effects that I would like you to really understand it, because it's very prevalent now out there. It's dependent on what you refer to as a pyroelectric effect. And pyroelectric effect, is based on materials, that change polarity if you induce them with pressure, temperature, or even any form of strain. If you bend the material, there is change of polarity, because the electron distribution in that material, changes. Okay, so these are materials really with a dipole moment, meaning if I apply some form of pressure, there is distribution, within, there's distribution of electrons, within that material, and that creates, potential difference, that you can actually measure. And that's what you refer to as, pyroelectric effect. So materials that have got, a dipole moment, and which gets affected, whose charge distribution, get perturbated, if you induce it with pressure, or temperature. Now, the most common type of material out there, is this type of crystal called the triglycine crystal, sulfate crystal, which tends to have pyroelectric effect, okay? And it's used a lot, for IR transducers, okay? But you're going to see in nature, there are many types of materials actually with pyroelectric effect. And I'd like you guys to go and check in the literature. For example, certain type of bonds, have got pyroelectric effect, meaning they can generate electricity. Certain types of wood, like cellulose, in fact, nanocellulose, has got, what you refer to as pyroelectric effect as well. And so these days you've got all these materials, that researchers are trying to study with pyroelectric material effect. And as such, you can actually use them for generation of small amounts of electricity. But in this case, anyway, I'm talking about, its effect, pyroelectric effect as a basis, for the IR transducer. But I hope all of us understand that. So the other type of detector for IR is just simply a diode array, a photodiode, as I've explained it before. Things like, mercury telluride, cadmium telluride, it's a very, very common, it's a semiconductor you can see. And because, as I've said, the valence band is not very far from the conductive band, even heat, from IR, can simply cause that transition. And so that you can be able to measure the current, that is being generated as heat or IR is impinged on a photodiode material. So in the next lecture, we're gonna now talk about very quickly, the different types of atomic spectroscopies, very quickly the components specifically of AAS, the components of AES, and so on, and that way we're gonna complete this chapter.